apparently I've not done a separate sympathetic versus parasympathetic video in the past. And I talk about it all the time, which is why I think I've done it 100 times, but I haven't. And whenever we talk about neuroanatomy, I tend to introduce everything, don't I, before we get there. But I'm going to do it. I think I'm overthinking it, because I talk about it all the time. I should just get it out. Because we're stuck at home, it's amazing how easily distracted I get.
That wasn't very good.
I've become amazed at my own procrastination. Right, we'll do it. We'll get it done. Okay, I'll do this every year, probably several times for the first years. How do I normally do this? Right, start at the beginning. So the central nervous system is the brain and the spinal cord. Everything else is the peripheral nervous system then, right? So the peripheral nervous system are nerves coming out of the brain, cranial nerves, and nerves coming out of the spinal cord. Spinal nerves. Lots of other bits and bobs as well. Okay, so far so good. And then we have, we might divide the nervous system up into somatic, soma, body, so somatic is of the body, and autonomic. So autonomic's like your automatic stuff. So somatic. Let's think about muscles. So there are 3 different types of muscle cells, aren't there? There are skeletal muscle, smooth muscle, and cardiac muscle. Cardiac muscle is only found in your heart. Skeletal muscle is the stuff that's generally attached to bones and lets you move. And of course this is stuff you can think about, you can control. And it's not just the muscles that move the limbs and bones and that sort of thing, but also of course the diaphragm. You can think about moving your diaphragm. So that's also skeletal muscle. So the skeletal muscle then is under somatic control. You can make it do something if you think hard enough about it. Cardiac muscle then. Cardiac muscle is under autonomic control. Whilst you might be able to like relax yourself and excite yourself to change your heart rate, you can't directly change your heart rate, can you? You could barely perceive the rate at which your heart is beating. So that's under autonomic control. And then all the other smooth muscle in the body, so smooth muscle is surrounding and lining arteries, you know, arterioles. It's lining most of the tubes of the body, you know, the GI tract. Glands usually have a muscular component that makes them squeeze things out. All of that smooth muscle then, you can't think about passing stuff through your GI tract. That's all under autonomic control. So somatic nervous system, skeletal muscle, autonomic nervous system, smooth muscle, and cardiac muscle. The autonomic nervous system gets divided up, and you'll read about different ways of dividing it up. It might be divided into 2 divisions, sympathetic and parasympathetic, or it might be divided into 3 divisions, sympathetic, parasympathetic, and enteric. You might even read about the visceral afferents, the sensory nerves of the autonomic nervous system, as being a separate division. So don't get confused by that. Sympathetic and parasympathetic neurons, they're all motor. They're all driving the smooth muscle and cardiac muscle, or stuff related to it. The visceral afferents are carrying sensation from viscera back to the central nervous system. So somatic afferent fibres, somatic afferent neurons are carrying sensations from the skin, stuff you're kind of generally aware of, stuff of the body, back to the central nervous system. The enteric nervous system gets referred to as kind of like your other brain. It's almost like a separate nervous system for the gastrointestinal system. It's got motor stuff, it's got sensory stuff, it's got reflexes and plexuses and interconnections and all sorts. And essentially what the enteric nervous system means is that the gut, the GI tract, has its own bits of the nervous system, so it can regulate and monitor and make it do its own thing itself without other parts of the nervous system getting involved, although those other parts of the nervous system can get involved if they want to. but we're going to focus on the sympathetic and parasympathetic divisions. So the sympathetic and parasympathetic divisions are divisions of the autonomic nervous system. The sympathetic nervous system goes everywhere in the body because it goes with all the blood vessels. The parasympathetic division is restricted to the head and the torso. If you've read anything about the sympathetic and parasympathetic nervous systems, you've probably heard that the sympathetic nervous system is associated with a fight or flight response, and that the parasympathetic nervous system is associated with rest and digest functions, which generally speaking is a great way of describing the two divisions. It's not the entire truth, but it's pretty good. You might also think of the sympathetic nervous system as expending energy and the parasympathetic division as conserving energy or restoring energy. They sometimes work in opposition, but not all the time. So the more you look into the systems of the body, the more you'll see how some areas fit with this idea and how some areas don't. Okay, if we take the sympathetic nervous system first, a good example is the heart. The sympathetic and parasympathetic divisions of the autonomic nervous system both innervate the heart. Now, fight or flight, sympathetic nervous system, what's that going to do to the heart then? Now, the heart has its own nerves and its own pacemaker system, so it beats at a regular rate. But if the sympathetic nervous system is applied to it, it will increase the heart rate and it will increase the force of contraction. So the amount of blood being pushed around the body will go up. The sympathetic nervous system will also cause dilation of the pupils. It'll actually also cause your eyes to widen because it pulls on one of the muscles up here. It will cause, because as I said, the arteries around the body, they've got thicker walls because they've got smooth muscle in their walls. The sympathetic nervous system can cause more blood to flow to your skeletal muscles. And it can cause the sweat glands to secrete sweat and things like that. And a whole bunch of other examples as well. But what about the anatomy then? Okay, so both sympathetic and parasympathetic divisions of the nervous system are two neuron systems, right? So they've got one neuron that's inside the central nervous system, sends out an axon, which then will find a second neuron, which will then go to the target organ. So there are two neurons between the central nervous system and the target organ for both sympathetic and parasympathetic stuff. So in the sympathetic division then, in the spinal cord, in the thoracic levels and the first 2 or 3 lumbar levels, in the grey matter, there's a little lateral horn you might be able to find. And in that lateral horn are the nuclei of the preganglionic sympathetic neurons. Preganglionic because they're going to run out of the spinal cord to a ganglion. A ganglion is a collection of nerve cell bodies. That's where the second neuron's going to be found. Okay, so the preganglionic sympathetic neurons cell body is in the grey matter of the spinal cord. It's going to run out through the ventral root of the spinal cord and then the ventral ramus of the spinal nerve. And we're going to see a white ramus communicans at each of those spinal levels come out of the spinal nerve and run to the ganglion. So the ganglion then is a little blob, a little bleb, a mass of neuronal cell bodies. So this white rami communicans, ramus is a branch, white because these neuron axons are myelinated, so they're white, right? Rami communicans, communicating, right? It's communicating to the ganglion. So that's the route that the preganglionic sympathetic neuron takes out to the sympathetic ganglion, or the sympathetic trunk, or the sympathetic chain, because there's a chain of these ganglia all the way down the posterior thoracic wall, abdominal wall, pelvis, up into the neck and what have you. But how does that work? As I said, it only comes out of the thoracic levels and the first couple of lumbar levels. Well, those preganglionic sympathetic neurons might go to the ganglion at the same level and then meet a second neuron, which would be the postganglionic sympathetic neuron, which will then run off to its target organ. Or they might not do that. They might go up a few levels or down a few levels, or they might run out to prevertebral ganglia, so there are other sympathetic ganglia in the body, and then meet that second postganglionic sympathetic neuron. So in that way, and there's some cool embryology here which we're not going to go into, we have sympathetic ganglia at pretty much all levels. And somehow a preganglionic sympathetic neuron is going to get to that ganglion, meet another sympathetic neuron, which will become the postganglionic sympathetic neuron. Now in some cases, that postganglionic sympathetic neuron is going to pass back to the spinal nerve at that level. And that is the grey rami communicantes. Grey because the second neuron, the postganglionic neuron, is not myelinated. Which means that the spinal nerves have all got sympathetic nerves running within them. So spinal nerves tend to be mixed. Somatic motor, somatic sensory, sympathetic motor, visceral afferents and all sorts, right? They're very, very mixed. Or those sympathetic neurons might take another route, splanchnic nerves or following big blood vessels or all sorts, but that postganglionic sympathetic neuron is then going to run throughout the body, which means some of them are very long because they're going to run all the way to your big toe, which is quite a long way away. So far so good. Okay, let's chuck in a little bit of neuroscience on top. The synapse, so the connection between the preganglionic sympathetic neuron and the postganglionic sympathetic neuron, that chemical connection is acetylcholine is released by the first neuron, and it meets nicotinic receptors on the second neuron, on the postganglionic neuron. Now that second neuron, the postganglionic sympathetic neuron, when it gets to its target organ, it's going to release noradrenaline or norepinephrine if you're in North America, and that will bind to adrenergic receptors on the target organ. Alright, that's the chemistry. And the thing to chuck on top of that then is the other organ of the sympathetic nervous system are the adrenal glands or the suprarenal glands. They've got a bunch of different roles, but the medulla, the central part of the adrenal glands, is a modified collection of sympathetic neurons, and they release adrenaline and noradrenaline. It's the adrenal glands, that's where all the names come from, right? And you know what that does? That goes into the blood, swirls around your body, and bam, switches on all those adrenergic receptors, and you're ready to go. You are fired up. That is your fight or flight response on. The parasympathetic nervous system is, generally speaking, a bit more chilled out. The parasympathetic nervous system, again, it's a 2-neuron system. You've got your preganglionic neuron and your postganglionic neuron. So your first neuron comes out of the central nervous system, and it can do that either in the brainstem, which means those preganglionic parasympathetic neurons are going to run out with cranial nerves, doesn't it? Because cranial nerves come out of the brainstem. Or they come out of the sacral part of your spinal cord. So S2, S3 and S4 levels of your spinal cord have preganglionic parasympathetic neurons in them. They're going to run out with what get called pelvic splanchnic nerves. Now the difference here is the ganglia, the parasympathetic ganglia, are not nice and neatly arranged like the sympathetic ganglia. The ganglia tend to be really close to the target organ or in the wall of the target organ. That preganglionic, postganglionic neuron meeting is often actually in the wall of the target organ. So what happens at the heart then? So if we compare to the sympathetic nervous system, in the heart, the parasympathetic nervous system will do the opposite. It will reduce your heart rate, reduce the force of contraction, hence conserving energy, do you see? It can also increase blood flow to the GI tract rather than to the muscles, so that after a heavy meal, when the GI tract really needs to get active, that's the parasympathetic nervous system partly stimulating it. It can increase the secretions of the glands into the into the GI tract. Good example of this is your salivary glands, right? When you smell food, your salivary glands start secreting. That's parasympathetic innervation causing those to secrete. And of course, these are the cranial nerves that we're talking about. Parasympathetic innervation will cause constriction of the pupil. So it's another good example of how sympathetic and parasympathetic innervation can work in opposition. But remember, it doesn't happen all the time. So cranial nerves 3, 7, 9 and 10 carry parasympathetic innervation from the brainstem out. So cranial nerves 3, you think eye. 7, that's the facial nerve, that's the snotty, dribbly, weepy nerve of the face, so it's innervating some of the muscles of some of the salivary glands. Cranial nerve 9, but cranial nerve 10, the vagus nerve, that's the big one. The vagus nerve is the wandering nerve. It passes from the brainstem, down the neck, into the thorax, follows the esophagus, through the diaphragm, into the abdomen. So it's the vagus nerve that carries much of the parasympathetic innervation from the central nervous system all the way up here, well here, down to the abdomen. And those fibres can get to the kind of the superior part of the pelvis, but then it's the pelvic splanchnic nerves that come up from underneath, from the S2, S3, S4 sacral levels of the spinal cord, that can then innervate the rest of the pelvis. Do you see what I mean? So it's the vagus nerve and the pelvic splanchnic nerves coming from the two different directions that mean that parasympathetic innervation can get to the viscera of the torso. So sympathetic innervation goes everywhere because it's going to blood vessels that control temperature regulation, heat loss from your skin, whereas parasympathetic innervation only goes to your head and torso. Thorax, abdomen, pelvis. Chemistry, right. So again, you've got preganglionic parasympathetic neurons meeting postganglionic parasympathetic neurons, and at that synapse we again have acetylcholine being released from the first neuron and meeting nicotinic receptors on the second neuron. When the second neuron, the postganglionic parasympathetic neuron, meets its target, that also releases acetylcholine, but onto muscarinic receptors, usually in the target organ. Again, this is what's up, seagull? This is what happens most of the time, but not all the time. Okay, finishing off with visceral afferents. A lot of this is terminology, isn't it? And once you get used to the words, the rest of it's all right. Visceral afferents. All right, viscera, organs, afferents. So afferents are going back to the central nervous system. Efferents are going away from the central nervous system. So efferents then are motor. They're driving muscles. Afferents are carrying sensory information back to the brain. We understand. As far as skin's concerned, we understand this really, really well. But organs, not so much. So the visceral afferents are a part of the autonomic nervous system. It's stuff we don't need to know about, stuff we don't need to be aware of, but they're carrying important sensory information back to the central nervous system. So they might be carrying information about muscle tone in blood vessels around the body, so the body knows where blood's going to and where it's not going to. It might be carrying information about activity, like baroreceptors in the carotid sinus, pressure receptors or chemoreceptors, looking at the composition of blood. It might be looking at stretch receptors in organs, think about the bladder, that sort of thing. So these visceral afferents, they're important for a whole bunch of reasons, and there's some good anatomy here that I'm building up to. The visceral afferents take the same routes back to the central nervous system that the sympathetic and parasympathetic fibres take out. That is, that most of the visceral afferents run from the viscera back to the spinal cord with the sympathetic neurons at those levels. But in the pelvis, those visceral afferents tend to run with the parasympathetic fibres and those pelvic splanchnic nerves back to the S2, S3 and S4 levels. The vagus nerve does carry visceral afferents, the glossopharyngeal nerve carries visceral afferents. That concept, okay, that concept's important. I don't want to overload this, but that idea is good. So, sensory fibres run from the organs back to the central nervous system with sympathetic fibres and with parasympathetic fibres. That means that two things can occur. You can set up visceral reflexes then, which means you can set up this automatic system of controlling different bits of the body with reflexes without using any higher functions at all. Also, it means that you can feed information back to the brain, and the brainstem, or even higher levels, can act on that information and maintain the homeostasis of the body, or prepare you for fight or flight, or whatever. So that idea of visceral afferents, those sensory fibres going back, is integral to this concept of an autonomic division of the nervous system. But the other thing that happens is referred pain. You feel pain in parts of the body that the pain is not in. Heart's, a heart attack's a good one, right? So, yeah, your heart is there, good. The visceral afferents from the heart run back to the central nervous system, to the spinal cord with the sympathetic neurons. And you don't just feel pain localized to the heart, you feel pain when you have myocardial ischemia in the chest, but also it radiates over the left shoulder and the left upper limb, doesn't it? It radiates over there. That's referred pain. It's not entirely understood, but it seems to be that where visceral afferents enter the spinal cord, they enter at the same level as somatic afferents, sensory nerves from the skin. As we develop, as we grow, we get very used to this somatic information going back to our brain. We don't get used to pain from our liver, our gallbladder, our pancreas, because hopefully it doesn't occur very often. So when it does occur, the brain perceives the pain as coming from the skin at the level that those fibres entered the spinal cord. So pain from the liver, pain from the gallbladder, it's felt in a region of the body, in a region of the skin, that's not necessarily where the liver or the gallbladder is, because the visceral afferent fibres, the sensory fibres from that organ, have entered the spinal cord at a level that sensory fibres from the skin also enter the spinal cord, and the brain perceives that pain as coming from the skin because that's a bit more expected than coming from the organ. You can then map this. You can get, if you're working clinically, you will experience this, and you will almost predict it and expect it in patients who've had abdominal surgery, for example. And also you will look out for these. Patients will complain of pain here or pain here, and you'll think, it could be this, it could be. It clues you in to what's going on in that person's body. That's referred pain. Like I say, seems like a pretty fundamental bit of neuroscience, and it's still not fully understood and described. Good, eh? Good. I'm not sure if I did a very good job of explaining that or not, but it's because I do it so often, and when you get used to explaining it, you get really far away from learning it. But students seem to know what I'm on about. They go away nodding anyway. But that should be everything you need to know about the autonomic nervous system versus the somatic nervous system, the divisions and the concepts of sympathetic and parasympathetic, and a bunch of terms that you can then take away and go and learn lots more from. Alright? That was the plan. Can't believe I haven't done this before. Feels like I've done it 100 times before. Maybe I have in like lots of neuro videos. Anyway, see you next week maybe. Wish I could find someone else to do this.